G.3 implementation in partitioning. Yeah. After our discussion, so the first half we spent a lot of time try to understand the design ideas. Yeah. Because we look at from the problem solving point of view. Yeah. Yeah. Because we want to learn. So in the real world situation, we want to learn how to solve a computing problem. So we spent a lot of time and going through all the thinking process, the whole thinking process to find a solution. Yeah. Not just give you solution directly. Yeah. So, all right. So we, go through the whole story. Yeah. So now we have good understanding on the implementation. Here, let's say the implementation main steps. Okay, here I can only say main steps, yeah, because we still need to provide more details later. Yeah. Yeah. All right, let's go to the next step. Yeah. First, yeah, when we do the implementation, how about let us do some relatively simple implementation. Yeah. Remember, yeah, so here I want to recall we learned one problem solving strategy. When you solve a relatively hard computing problem, if you feel too hard, then we take this strategy. Can we solve a simpler version of that problem? Yeah, simpler version. We make it simpler. Yeah. We can modify our original problem slightly and make it simpler to solve as our first try. Yeah. We know we may not get the best solution in our first try. After that, then we do some further improvement. Yeah. So that's the commonly used problem solving strategy. Here, let's apply that strategy another time. So the first time, when we do the implementation, we want to make the situation as simple as possible for ourselves. Yeah. So what's that? Here I said straightforward implementation. Straightforward implement. That means we do not apply any special trick, any smart trick. Yeah, straightforward. I mean, just simple, direct steps. Everybody can understand easily. That's the straightforward implementation. Okay. All right. Yeah. So let's do it. This time, remember our goal, we want to split the given array into two subarrays, A subarray and a B subarray. Here, let us use two auxiliary subarrays to store A subarray and a B subarray. Yeah. Two auxiliary subarrays. Yeah. Because if we can use two auxiliary subarrays, then we can make our implementation easier. But here, two auxiliary we treat as extra resource. Extra resource. Here, we use some extra resource, yeah, to make our implementation easier. Yeah. All right. This is our original array, and we select the pivot element and we put the pivot at the end location. Yeah. Here you may ask me, do we just use the last element as the pivot directly, or we select arbitrary element in the array and then we swap it put it at the end. Yeah, both ways are fine. Both ways are fine. Yeah, but I want to make do discussion at the end. Yeah, after we finish everything. Yeah, here let us assume we just select the last element as the pivot. Okay, so we do not select arbitrary one in the middle, then swap it at the end. Later, at the end, when I talk about improvement, then I talk about that idea. Okay, yeah. So that is a improvement idea. Okay, yeah. Here we directly select the last element as the pivot. All right, yeah. Then we scan the array. What do you mean scan? Compare each element from left to right with the pivot element. Okay? You can imagine you run a for loop. When you get the current element, you compare it with P. If that value is less than or equal to P, you store it. You put it in the A auxiliary subarray. Remember here, A and B, we use two extra auxiliary subarrays. Two auxiliary arrays. Yeah. Array or subarray. Yeah. Two auxiliary arrays. Yeah. So if you find one element that is less than or equal to P, you just, put it in A array in order. Okay, the first one, second one. At the beginning, it's empty. Yeah. Then the first element, second element, and third element. Then if it's greater than P, you put in the B array. Yeah. So make sure A of I in A array is less than or equal to P, and A of I in, if it's greater than P, you put it in B array. That's simple, right? One scan, you can get it done, right? Yeah. From left to right, you follow the natural order. One scan, you can split your given data into these two auxiliary arrays. That's easy. Yeah. After that, yeah, because you want to put your data into the original given location, yeah, in order to do the recursive function call. So you need to copy the data from two auxiliary arrays back to the original array. Copy back. Yeah. Yeah. Copy. Okay? Data copy. Yeah. Back to the original array. Yeah. Suitable locations. Yeah. All right. That is, in that way, we did a partition, right? So we did the desired partition. Yeah. So the question is the solution acceptable? Is the solution you feel good enough in this way for one partition step? Yeah. So you make it. Yeah. Yeah. First, you make it. Yeah. Yeah. But we want to improve it. Yeah. Here, the reason we want to improve it, because look at here, we use extra resource. Extra resource, if you use extra resource, the more resource you use, the slower the whole algorithm. The reason is our memory resource is limited. The memory resource is limited. If in each step you need to use extra resource, then your overall performance will be slower due to the limitation of the memory resource. Okay? Yeah. So for that reason, in order to improve our overall algorithm efficiency, we want to reduce the resource used for our algorithm implementation to the minimum, or we want to eliminate this extra resource. We want to eliminate 2 auxiliary arrays. Do not use auxiliary arrays. Can you do the partitioning step? Can you do that partition step without auxiliary arrays? The next question. Yeah. So we just do the same thing, but this time we want to eliminate those 2 auxiliary arrays. Yeah. So that's our next improvement step. Yeah. Remove the auxiliary arrays. Yeah. All right. Yeah. So here, you can see it's doable, right? Yeah. But you need some smart idea. Yeah. To do it, you need some smart idea. Okay. Yeah. Yeah. But it's doable. Yeah. So you can feel it's doable. It's possible to make it happen. Yeah. All right. So here we need to control extra space used. Yeah. Here the point is control extra space used. Yeah. Yeah. When you implement every algorithm, you may need extra space here. What's the meaning of extra space? People may ask, what's the meaning of extra space? No. No. Some space we do not treat as extra space. No. The space we use to store input data and output data. Okay? So when you use the, because you need some minimum space. Minimum space to store input data and output data. Yeah. All right? Yeah. Yeah. That's the minimum space you need to use. Input data, output data. Okay? But other than that, you need some extra space to be used to manipulate your intermediate computing results, right? Intermediate computing results. Yeah. You need extra space. Yeah. But the issue is how to minimize the usage of the extra space. We don't want to waste a lot of extra space. Okay? So we want to use as little as possible extra space. Yeah. So here, control extra space used here. Yeah. All right. How to control it? Now we should manage the space in the original array in an efficient way. Yeah. So we need to carefully manage the variable space in the original array. Yeah, because we treat, so the space here, we not extra, right? Because the space here, it's the input space. When you have input data, you need to use this space to store your input data. So it's not extra space, okay? So if we use the input space, then we have no problem. We can use it whatever we want. Yeah. But other than that, you may need a little extra space. Yeah. A little extra space. Okay? Yeah. Yeah. But we want to control it. The extra space. Control not too much. Okay? As little as possible, not too much. Yeah. All right. In order to manage the input space in an efficient way, we want to use several different regions to store our data with different status. Yeah, because each element could be in different status, right? Yeah. Is it in A subarray? Is it in B subarray? Or is it in, unknown. Yeah, because sometimes an element in the array could be unknown. We don't know if it's in the A subarray or B subarray. We don't know. Unknown, right? Yeah. So that's the status or states of the elements of our data. Yeah. So here, first we define a region we call the S region. S means smaller or equal to P. Yeah. So the elements in S region, we place those elements in this S region if their values are less than or equal to P. Yeah. Yeah. S means smaller. Okay. Yeah. Smaller or equal. Yeah. S region. Then the second region to store those elements that are greater. L means larger than the element, than the pivot element. Yeah. So all the elements in this region, L region, have larger values than that of P element. Yeah. And the third region, unknown region, unprocessed. Yeah. Unprocessed. Yeah. Because when we process element by element, there are some unprocessed elements, right? We need to maintain one special region for those elements. So U region. Yeah. We just manage these three regions in a well-organized way. We can implement the partition step. So that's the details we need to add to this implementation in order to save as much extra space used as possible. That's the goal. Yeah. So, yeah. All right. Now, when we do the processing, for the A subarray, it corresponds to S region, and at the beginning it is empty. Yeah. B subarray, it corresponds to L region, and at the beginning it is empty. Yeah. Initially, these two regions are empty. Yeah. And every time when we process one of the elements, we grow one of the two regions. Yeah. Because after the processing, we will add the current element in one of these two regions. So we grow one of the two regions. Yeah. And for unprocessed region, initially, it covers the whole array except the P. Yeah. P. So it's not in any of the three regions. Yeah. So almost the whole array. Yeah. Other than P, yeah, the whole remaining elements. Yeah. Then at the end, the unprocessed region becomes empty. So we finish processing all the elements. Yeah. So in this way, you can see we eliminate those two auxiliary arrays. You do not need to use two auxiliary arrays. Yeah. But definitely, when you use these three regions, you may need to use some here. What's wrong? Here. I cannot roll. Oh, something is wrong. Yeah, my screen freezed. Oh. Oh, let me start over again. Yeah. Get to this point. Yeah, we are here. Oh, yeah, next one. Yeah, we are here. All right. Yeah, so let me move to G.4. All right. example for partitioning. Yeah. Now, oh, yeah. So yeah, my pen. Yeah. So let me change a different pen. Yeah, my pen has a problem. Oh, yeah. So I have a backup pen. So let me, yeah, my pen, I need to change the battery. Yeah. So here, let me use my backup pen. Yeah, this is backup pen. All right. Yeah. G.4, example for partitioning. Yeah. In this part, I show you a concrete example. Yeah. So at this point, we have the basic idea on the implementation of the partition step. But to see everything in details well, let me run a concrete example. You know, in the animation style, so that you can see the implementation better. Yeah. All right. So let me use this example. Yeah. Yeah. Look at the array with values like this. Yeah. And we use the last element 4 as the pivot. Yeah. And let's run one partition step. Yeah. One partition step. That's enough. Yeah. Here I only need to run one partition step. Because if you understand one partition step, you just write your code as a recursive function, then you can do any partition step by recursive function calls. Yeah. All right. Yeah. At the beginning, yeah. So we use different colors. Yeah. So here the pivot element has a special color, and the 3 different regions, each one has its own color, and a U region in white color, okay, or no color. Yeah, just yeah, that's U region. All right, and we need an extra space to swap, to do the swap operation. Yeah, so you need extra space. Yeah, but just the one location, that's not much, right? Yeah, so that's not much. Yeah, one extra space location. Yeah. All right. Yeah, let me run step by step here. Start. Yeah. When we start, let's initialize our S region to an empty set. L region, another empty set. Yeah. So then let's do the scan of the elements from left to right, one after another. Yeah. All right. Step 1, let's compare the current element 2 with the pivot 4, and we know it's smaller than the pivot, so we put it in S region. So we grow S region by adding this element 2. Step 2, compare, yeah, and we use yellow color for the S region. Yeah. Step 2, compare next element 8 with 4. It's greater than pivot. So we put it in L region, we grow L region, and we use green color for the L region elements. Yeah. Step 3, compare current element 7 with 4. It is greater than pivot, so we should grow L region. See? Very simple, right? Yeah. All right. Step number 4, 1 is less than the pivot. We should put it in S. So we should make this element yellow color, but there is a problem. Yeah. So look at the current state. Yeah. 2 elements in yellow color are separated by the green color region. That's not good, right? Yeah. In our design, we should make all the elements in yellow color in one S region occupying consecutive locations, right? Not separated by anything, okay? Yeah, so we want to move. So after this step, we should make an adjustment. We need to move element around so that all the elements in yellow color region occupy consecutive locations, yeah, and so on. All right, yeah. So can you see any easy way to make this happen? Yeah. You can do the swap operation. Remember, this swap space, we haven't used this swap space, right? Can we use this swap space to make an adjustment to, make the yellow elements in the same region occupying consecutive locations? Yeah. A simple way is we do swap. Let's swap element 1 with one element that is adjacent to 2. Swap 8 and 1. Yeah. Okay. We just want to swap element 8 and element 1 using that extra space. After the swap operation, you see element 2 and element 1 are adjacent. Yeah? Adjacent. So one swap operation is used in this situation. Okay? Yeah. So now we grow. We have a nice S region and nice green region. Yeah. Yeah. So they all occupy consecutive locations. Yeah. All right. Step number 5, compare 3 and pivot. 3 less than the pivot. So it should be in S region, and we color it in yellow, but we want to swap element 3 with element 7 to get desired situation. Okay? Desired situation. Yeah. All right. So that's step 5. Then step 6, last element for the comparison. Compare 5 and 4. It should be in L region. Yeah. So you can see every time when we get an element in L region, we do not need to do a swap, right? Yeah. So you can see every time when you get a element in L region, except the first one. Yeah, if the first element is in L region, you do not need to do a swap. Okay? Yeah. We can say if you get the first element in S region after after you have at least one element in the L region, then you need to do a swap, right? Yeah, think about that. Okay, think about that. Yeah, yeah. Because in my homework assignment, I will give you a question, ask you count the number of swaps you need to do in one partition step. I may ask you count how many swap operations you need to do in one particular partition step. Okay? Yeah. So you need to understand, you need to see under what situation we need to do a swap operation. Under what situation we do not need to do any swap operation. Okay? All right. Yeah. After that, then we complete the partition step. Oh, I can say we almost complete. Yeah, because there is last thing we need to do. We haven't put this pivot in place. We haven't put this pivot in place. Okay? Yeah. So we need to do another swap operation to put pivot in place. Yeah. I think you can see what is the swap to do to put pivot in place. Swap element 8 and 4, the last swap. Swap 8 and 4. After that, you put it in place. After that, you put the pivot in place and you complete one partition step. Yeah. After this step, now you can see all the elements at the left-hand side of the pivot are less than or equal to 4. Yeah. We allow, so if you have element equal to 4, we allow equal case. Okay? Yeah. All the elements that are greater than the pivot at the right-hand side of the pivot. Yeah. So that's the whole process of the partition step for the quicksort. Yeah, so you can see, yeah. With this example, so you can see the implementation details very well. Yeah. All right. Yeah. So next, yeah. So we have some small technical things we need to consider when we write our implementation code. Yeah. How to grow S region and L region when you write implementation code. Yeah. So we just use two indexes to control, I index and J index. Yeah. S region. Yeah. So how do we define S region in the given array? Yeah. We use the A array location from 0 through I location for the S region. Yeah. L region, we use the A array location from I plus 1 through J for the L region. Yeah. So you can see, if you want to grow S region, you just increment I value. If you want to grow L region, you just increment J value, and so on. Okay? Yeah. Yeah. Before the final in place step. Yeah. So change I and J when you grow S region, grow L region. Okay? Yeah. Yeah. And when you swap two elements, also easy. When you swap two elements, you need to adjust I value, right? Yeah. Yeah. All right. So that's the implementation detail. After that, we need to look at the worst case and the best case. Worst case efficiency first. Yeah. All right. For the worst case, yeah, let's study the worst case. Yeah. The worst case. First, we need to look at under what situation we have the worst case. The worst case happens when the partition is extremely unbalanced. Yeah. Here we use our balancing principle again. Yeah. So remember, yeah, I mentioned that balancing principle. Yeah. So when you have chance to distribute your data, so here the partition actually it's hard to control. How do we distribute the data? But we just look at the result. If after our partition step, we end up have an unbalanced arrangement for two subarrays. Yeah, unbalanced. Yeah. One subarray is very small, the other subarray is very large. The difference is big. Yeah. So we treat as an unbalanced data arrangement. In that situation, it should correspond to the worst case. For example, here, other than P, all the elements are in the yellow region, S region. Yeah, it's unbalanced case, right? Yeah, yeah. Yeah. So here, we can call S case. Yeah. So all elements other than P are in the S region. Another extremal case, all the elements except P are in the L region. Yeah, we can call SL case, and so on. Okay, so we have these two types of extremal cases. Yeah. If in each partition step we have one of the two extremal cases, then we will end up with worst case. Yeah. If we run this quicksort, we will end up with the worst case efficiency. Yeah. All right. Yeah. Yeah. Both cases we use n-1 comparisons. Yeah. And how many swaps? Yeah. So here we do not use swaps. Yeah. 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 Because here our basic operation is the comparison operation. Basic operation. Swap operation is not the basic operation. Okay? So when we study the efficiency, we only look at the comparisons. We do not look at the swap when we study the efficiency. Yeah. All right. So if you look at the number of comparisons in the extremal cases, these two extremal cases, and you also need to imagine when we run all the partition steps, we always have one of the two extremal cases. Then we will have the worst case at the end. Okay. Yeah. All right, right? Yeah. Although you can argue, one of the worst cases is slightly worse than the other if you really want to compare. Yeah. Because in the second one, you need to do a swap, right? At the end, you need to swap P with the first element to get it in place. The first one, you do not need to do a swap. Okay? So you can argue the second one is slightly worse than the first one if you look at the swap operation. Comparison, they use the same number of comparisons. But the swap operation, they use different number of swap operations. Yeah. So slightly better or worse. Yeah. Yeah. All right. Yeah. Then let's look at the recurrence relation for the worst case. Yeah. All right. So the running time complexity function, let's use T. Actually, we use T represent the number of comparisons for the quicksort. Okay? T of n. Yeah. T of n. Number of comparisons. Yeah. T of n equals T of n minus 1 plus n minus 1 comparisons. Yeah. So here, let me explain why we have this formula. Yeah. This T of n minus 1, because after one partition step, you reduce the problem size by 1, right? Yeah. So the next round, you need to solve the same problem with smaller data size, the size n minus 1. So you need to have this T of n minus 1 for the remaining work. Yeah. But to get a partition, you need this many comparisons. Okay? So that's for the partition step. Okay? The partition step has this cost. Okay? So that's why you have this recurrence relation. Yeah. But if you want to calculate this recurrence relation, it's very simple. You just keep doing the iterations and you will get, yeah, because 1 plus 2, yeah, plus, yeah, minus 1. Yeah. Every time you reduce the problem size by 1, and after that your partition is the extremal case, one of the two extremal cases. Yeah. So you have this, your worst case efficiency, you have this efficiency function. Yeah. So that is in the big theta of n squared. That's the case for the poor worst case efficiency, right? Yeah. So we talk about what is the poor efficiency, worst case efficiency function. So this is the poor one. Yeah. So the quicksort cannot avoid the poor worst case efficiency. Quicksort cannot. Okay. Yeah. But the quicksort, its overall average case efficiency is, you know, we can say close to the best. Oh, yeah, yeah, among the best. Yeah, yeah, yeah. All right, yeah. So that's the main reason people use the quicksort, yeah, because it has the excellent average case efficiency. Yeah. All right. Then, yeah, example for the worst case. Yeah. So here I just, show you some special example for the worst case. This one, the given array is in descending order, right? So this example, the given array is in descending order. Yeah. So then, after one partition step, after we swap the pivot in place, yeah. So then we need to run another partition step, okay, like that. Okay. Then another partition, yeah. Yeah. So we put one more element in place, yeah. So then the next partition step, yeah. All right, yeah. So and yeah, another step. Yeah. Every time we put one more element in place. Yeah. So at the end we put all elements in place. Yeah. So this corresponds to the given input in descending order. Yeah. This is in the descending order. Yeah. So what do you expect when your input data is given in descending order? Yeah. So this example tells you what you will see if the data in descending order. All right. So next, let's consider the best case efficiency of the quicksort. Yeah, the last topic of the quicksort, the best case. For the best case here, after every partition step, we want to see the two subarrays are of almost equal sizes, yeah, as equal as possible. The sizes of two subarrays as equal as possible. Yeah. So most balanced partitioning. Yeah. So S region, L region, have almost the same size. Yeah. So here you can see, yeah, we can write our recurrence relation in this way. Yeah. After the initial condition, the recurrence relation, because we need to conquer two subproblems. Yeah. Each one of half the size, half problem size, but you need to conquer. So here, the conquer step. Conquer step, so that's why we use this 2 times. You need to call recursive function twice. Okay, first on left subarray, second right subarray. So you have this 2 times t of n over 2. Then the combine step. Combine step, actually, we can put n here. Yeah, n comparisons. Yeah, n minus 1, we use approximation n comparisons. Okay, yeah. Our textbook uses this theta. Okay, theta of n. Yeah. Yeah, actually, we can use n here, n comparison. Yeah. Then, when you look at this recurrence relation, is it the same as our merge sort one? Remember last time when we talk about the merge sort, we derived this recurrence relation. There I said I delay the discussion to the quicksort. Here you see in the quicksort, for the best case, most balanced partitioning, for the best case, we have this same recurrence relation as our merge sort. Okay, yeah. So that's why we combine our understanding for these two cases combined to one. Yeah. So we only need to do discussion once, combine the two situations. Yeah. All right. Yeah. So yeah, here the constant, but here our constant is 1 here. Okay. Yeah. Some constant. Yeah. 1. All right. Yeah. So here I want to use a recursion tree to show you the estimation idea. Yeah. Recursion tree. Here we do not do the math. Okay. Yeah. Yeah. Although we can use math to solve this recurrence relation problem, yeah, but we need to do a lot of work. Okay. So here we just draw a recursion tree and use the structure of the recursion tree to estimate the total cost for the runtime efficiency function T. Yeah. All right, let me show you the idea. Okay. Yeah. When we draw the recursion tree, let's assume the data size n is between two adjacent power of 2. Power of 2. Yeah. Every positive integer we can find two adjacent power of 2 such that this positive integer is between those two numbers. Yeah. Yeah. That's easy to see. Okay. Yeah. So although I can draw a diagram to show you. Okay. Yeah. So if you really ask me to prove it, I can draw a simple diagram to show you here. Okay. All right. So when we start 2 to the 0, it corresponds to 1, right? Because we consider positive integer. So the starting point is this 1, okay? So we want to cover all positive integers on this line axis, all right? So let's look at the next point. 2 to the first, 2, okay? 2 squared here, 2 cube, and so on, okay? 2 to the k, 2 to the k plus 1. All right? Yeah. Because the right bound could be equal, included. Right bound could be equal. Right? Now you you select any positive integer, it must fall into one of the interval, right? So you have interval 1, interval 2, interval 3, and so on. Okay? Yeah. And any integer n must fall into one of the interval, right? So this is the interval this given n falls into. Yeah. So we can always find one interval that covers the given positive integer n. Yeah. So that's our understanding. Okay? Yeah. The reason we want to find this interval because we want to estimate how many levels do we have in our recursion tree. Yeah. So let's take some basic operations. So we get n over 2 to the k plus 1 is between 1/2 and 1. That corresponds to the data size after the split, right? Remember, we do the n over 2 split. So data size Okay? If the data size is less than or equal to 1, that means we need to stop splitting, right? That's the end. That's the, the bottom of the tree. Yeah. The leaf of the tree, the bottom of the tree. Yeah. Now let me draw the recursion tree. Okay? Yeah. Draw recursion tree. Yeah. So this theta of n, we use constant c times n to represent. Constant c times n to represent. Okay? Yeah. All right. So then, in each level, we only collect non-recursion cost. So this cost we call the non-recursion cost. Yeah, because this is the recursion part. Okay, this is the non-recursion part. Non-recursion part. Okay, so in our tree, we only collect non-recursion cost each level. Okay, yeah. The second level, non-recursion cost. Because the recursion cost, when we accumulate all the non-recursion cost, we will get the recursion cost. Okay? Yeah. So at the end, we just accumulate all the non-recursion cost. Yeah. So we get a total recursion cost. Okay? All right. So each level, let's add the total cost for each level. Yeah. Top level, C of n. This level also C of n, right? C times n. This level, 4 terms adding together, also C of n. So same, so you can see each level, same non-recursion cost in each level. Yeah. But how many levels do you have, right? Yeah. You count how many levels, approximately k, right? Approximately k levels. Yeah. It could be k plus 1, but for k plus 1, we can use k approximation, right? Yeah. The plus 1 is not important. So we just use k approximation. So you have approximately k levels. And that k is approximately equal to log n, right? K approximately equal to log n. So the total non-recursion cost adding together, you have n log n. Big theta of n log n. Yeah. That's the way we use the recursion tree to estimate the total cost, from a recurrence relation. Yeah. Yeah. This way much easier. Okay? This way you do not need to do complicated math computation. Yeah. You just estimate drawing this tree. Yeah. Yeah. So this is a useful method to do analysis. Okay? Yeah, recursion tree. Yeah. All right, so then I finished this Quicksort topic. Yeah. So now we have everything we need to learn about Quicksort. Yeah. So I only have 6 minutes left. Yeah. For the remaining only 6 minutes. I cannot do more discussion. Yeah. So let me delay the selection problem next time. Yeah, later time. Yeah, later time. Next week, I want to cover module 5 first. Yeah, I think two classes should be enough for the module 5. Then in the review session, yeah, remember, before the final, we have one class we use for the review session. Okay, so for the review session, I can talk about review questions. Yeah, and I will use about half an hour to talk about the selection problem. Okay, finding the median of 5 elements. Then I talk about the general selection problem. in the review session. Okay, yeah. All right, yeah. So let me stop right here.